It's my great pleasure to introduce Nirmal Narotam, who will be giving tonight's talk on practical guide to the management of bad actor alarms. Nirmal and I worked out that we've known each other since about 2000 when he was working at what was then called Polyfin in the Midlands plant in Sasolburg, and we've stayed in touch ever since. He's currently the managing director of PAS in South Africa. His educational background is also KZN, where he did his bachelor's and his master's. And then I see he did a LLB at UNISA as well. And Nirmal very much specializes in this field of alarm management and is certainly a specialist in it. So I'm not going to talk anymore. I'm going to hand over to him. What I would ask people is, if you've got questions, please put them in the chat. If you don't want to share your question with everybody, then just in the to box there, make it to me, to Kevin. And I will respect your anonymity in asking the question. With that, over to Nirmal.
Thanks, Kevin, for that kind introduction. Yes, we've known each other for quite a long time now. Today I'm going to talk about alarm management and specifically bad actor alarms. I think people will find this talk quite interesting. I've been busy with alarm management professionally since 2005. That's about 16 years. I've helped customers all over the world with this problem. And it's strange that the problem still persists. We will find out during this talk that it's not a one-dimensional problem. It's not a technical problem. It's a problem more of human behavior, which is something that engineers tend to not be good at, if you guys get my drift. So let's get started. As usual, we always start with our agenda. So I'm going to start with the alarm management problem as what it really is. We're going to do a little case study, and I urge you guys to make screenshots of the little case study, because right at the end, we'd revisit that case and we'd come up with what would be the correct solution. And then some toolkits on bad actors. So let's get started with the issue. Back in the day, 1960s and so forth, our operators were faced with maybe less than 500 tags or points that they would monitor. And they typically monitored these on panel boards and large equipment. As time went on, technology caught up and DCSs became more popular. And we obviously gave our panel operators a lot more to look at. Coupled with that, the cost of adding an alarm dropped substantially. Previously, you would need a loop drawing, or you would need a Omni 16 panel with lamps and all that stuff in order to produce an alarm. In today's world, all we do is we click a checkbox and we have an alarm. And what happened was that we found that after a few accidents and incidents, that the operators were faced with quite a lot of alarms. On a typical factory, an operator would get 2,000 or 3,000 alarms a day. I'm actually being kind right now. I have seen plants with 50,000 alarms in a day. So in the ASM consortium did a study, and they found that an operator, highly skilled, experienced, could only handle about 300 alarms per day. That would be the maximum. 300 alarms per day is about 12 alarms an hour, or about 1 alarm in every 5 minutes. Now, if you go to some control rooms in the factories, you would find operators are getting alarms continuously. And clearly they have no way of knowing which alarms to ignore and which alarms to respond to. Second issue we found is that operators receive alarms at a very high rate. We call this an alarm flood. Alarm floods occur when the alarm rate exceeds 10 alarms in 10 minutes. 10 alarms is not a lot. And 10 alarms in 10 minutes means the operator would immediately start ignoring alarms 10 onwards. So alarms 11, 12, 13, 14, the operator will forget about those. In this particular example data, you would find that the system was flooded for 6.9% of the time. That means your process alarm system was not available for 6.9% of the day. That's a very, very high amount of unavailability. Typically, when we design a control system, we're looking at availabilities of 99.99%. It all came to a head back in 1994 when we had a major accident at the Texaco refinery. Tragically, 10 people perished. And part of this particular incident was the alarm system. The alarm system itself was not the only cause of the problem. There were other causes like design issues and so forth. But the reality is that the alarm system did play a major role. And in particular, it was a stale alarm on the level of the column. And we'll look at stale alarms going forward. But what we do realize is something needs to be done about this problem. And companies like PAS have been operating for about 20 years now, looking at alarm management. But the solution to the problem remains elusive. It's not an obvious solution, and it's not a solution that you can put into a textbook because it involves a lot of other factors that are not purely engineering kind of factors. So let's get stuck into our case study, which is quite interesting. So what we have here is a surge drum with the input flow to take the surge. We have a level indicator. We have a pump with the start permissive at 35%. In other words, operator cannot start the pump until the level is greater than 35%. The pump trips at 30%. The trip was included because the expectation was that the supply flow would drop periodically more than once per annum. If a circuit is expected to operate more than once per annum, that circuit is considered a control circuit and not necessarily a trip circuit. We have a discharge pressure on the pump to tell us what the discharge pressure is, and we have a flow controller to tell us what the flow to the subsequent downstream unit is. The designers of this plant were concerned about this pump because this pump, if it runs with no suction, could start cavitating and it would eventually leak, releasing material into the atmosphere. So they put in a trip circuit so at 30%, the pump would stop automatically. So the next few steps occur almost in every design study that I've ever been. So we asked the question, what alarms do we need for this particular facility and so forth? And we would get stuff like this. The operations will say, let's put an alarm on the interlock when it activates, because operator needs to know. Fair enough, I guess we could include that one in. Control systems will say, we always alarm at the trip point and at the highest priority. And you'd find this in specifications of major oil companies, oil and gas, mining, and so forth. We always alarm at the trip point. That is what they say. The next group is rotating equipment. And they make a good point. They say the supply of the pump has specified an alarm at 45 kPa. So we add that alarm. We cannot argue with the supply of the equipment, of course. And the process safety people speak of RCA means root cause analysis. Speak of root cause analysis recommendations, where we need to have a low level alarm on the tank. And it's specified at 35%. So that alarm is included. And it's always the project manager that speaks last. The project manager sends an email to say, we should always have alarms on pump stops. So every one of these participants have a really good intention in the sense that they're worried about different things and they're worried about outcomes that would actually cause harm. So we end up with a situation like this. I advise you guys to take a screenshot because I'm going to branch off into another software, a simulation software, to see the effect that this type of alarm system would have on an operator. So everyone felt really good after the study. They all slept very well at night because they believed that they have given the operator all the tools the operator needs to protect the plant. So this is a dynamic simulation of the same facility. I've inserted a control valve in here to shut off the suction flow. And let's see what happens when a perfectly normal condition occurs, and that is loss of supply. So the event that we're talking about is a loss of supply into this particular. So now that I've reduced the flow to zero, you would notice that the tank level will start dropping. And the first event that would happen would be the interlock will activate at 35%. Here we go. And the next event that would occur would be the pump will trip at 30%. Here we go. The discharge pressure has dropped and the flow has dropped to zero. And you notice that in this particular sketch, we have 1, 2, 3, 4, 5, 6 alarms that has informed the operator that something's happened. Yet, there's nothing unsafe or abnormal about this condition because the plant designer wanted all of the stuff to happen. Nothing that has happened so far is abnormal. If you look at the operator's alarm display, you will notice that his alarm panel has lit up like a Christmas tree. But yet, he has no actual action to take. There's zero action for the operator. All he has to do is acknowledge all these alarms. Let's just go back here and talk about the real danger. So I'm going to reset the simulation. And I'm going to talk about the real danger. So we rerun the simulation, but this time we have a fuse relay on the pump, which means that even though the level drops, the pump does not get the stop signal and continues operating in a dangerous condition. So again, the moment the flow drops to less than 5%, 5 meter cube per hour, operator is immediately worried about the downstream plant. So he would probably move off this page. And look what happens. Operator has received many alarms. Yet, because of past experience, operator will not respond to these alarms. And the pump will run dry, creating a dangerous condition. In this case, even the e-stop will not work because it's a fuse relay. So the only way for the operator to stop this is to go outside and manually stop it to prevent the incident from happening. So what we find out from this whole exercise is that even though we seem to have a lot of alarms protecting the plant, the alarms sound, the operator has no actions for a normal occurrence. And when the actual problem happens, we will not notice it. If you look at the alarm summary again, you would see that there's a whole bunch of alarms, yet it's very unlikely operator will pick up this problem. So right at the end, we'd go back and revisit this issue with the correct alarm setting. So back to our slideshow. What lesson do we learn from this whole thing? Well, it seems like this guy, Henry George Bond, knew a thing or two about alarm management. He says the road to hell is paved with good intention. Every single participant in the meeting believed that they're doing a good thing. And in the end, we realized that actually did not help the operator at all. The second point we learned is from Master Yoda from our Star Wars. And we always turn to Master Yoda when we need assistance. Train yourself to let go of everything you fear to. Every participant believed that if they do not put in their alarm, then they will put the plant at risk, and it allowed them in isolation to sleep well at night. But what we learned from this whole experience is that alarm management is a behavioral issue. It's one of culture and less of engineering. So if you look at the work process of alarm management, it's quite complex. There's alarm philosophy that's required. There's a whole bunch of operational activities that have to happen on a monthly basis. There's design work that has to happen. And there's periodic system audits that have to happen. And I think if you're serious about alarm management, you have to do these things. But if you need results quick, literally two things that need to happen with any system that's generating too many alarms. The first thing is the redesign of the alarm system. And the second one is the bad actor rationalization. I'm going to touch a bit on design aspects of alarm rationalization, but it's a fairly complex and long topic, and there's not enough time for that. But in terms of bad actor rationalization, I think we can get through some of the material today. So let's look at the three commandments of alarm system design. And this is probably your go-to three commands when you have a choice as to which alarms to include and which alarms not to include. The first commandment, thou shalt only alarm if an operator action is required. What does that actually mean? Well, let's go back to our problem that we discussed. When the tank level dropped and the pump stopped, the system did exactly what it was designed to do. There was no operator action. All the operator had to do is acknowledge the alarms, and that's not an operator action. There was absolutely nothing for the operator to do. We had broken the first commandment immediately. There was an operator action for the flow, by the way, but for the tank, there was no action. And most of the alarms were centered around the tank. Second commandment, thou shalt only alarm if the situation is abnormal. Let's go back and have a look. What was abnormal about the situation? Yes, the flow dropped. That was abnormal, and there was an alarm for that. But whatever happened after that was perfectly normal and expected and should have happened, and happened as it should. We noticed the level started dropping, the level alarm came up, but it shouldn't have come up, but the level started dropping, the pump stopped, and so forth. And that's really the second commandment. The third commandment is probably the commandment that gives the biggest benefit. You shall not duplicate alarms. No two alarms shall have the same cause event. In order to meet this requirement, you need to do some dynamic analysis to achieve this. And this is where there's a mismatch between the different safety studies that are typically done in the plants. A hazard study, for example, is a steady state analysis by and large. Yet hazard studies are often used as a mechanism to create alarms. So let's look at this. No two alarms shall have the same cause event. So let's go back to our little example and have a look. We notice that, for example, this low flow can be caused by a multitude of factors. The first factor is loss of supply coming from the FI01. It can also be caused by this pump stopping. And it can be caused by this valve closing when it's not supposed to. So if you want to retain this alarm, you have to make a choice between the other. In my view, the best one is the flow, because the flow will give you a very early indication that this flow will drop. Of course, the pump could stop as another cause, or the valve could close. And we will discuss this in more detail. But that's how you do a cause analysis for your various alarms. And the moment you find that you do not have unique causes, you need to remove those alarms. Because all they would do is they would give an operator 2 indications of the same event. And remember, we only have 10 alarms in 10 minutes in terms of our specifications. Let's just go a bit deeper into the alarm design problem and what it truly is. On this little graph of mine, there's a probability of an operator failing to mitigate the abnormal situation. So there's an event that requires operator attention, and there is a possibility that the operator may not act on that event. So we can start with giving the operator absolutely no alarms, 0 alarms, nothing. He just operates the plant. Guess what? There's no guarantee that he will miss every event, because he's now very vigilant because he has knowledge that he has no alarms. It's like when I renovated my home, my alarm system at home was offline for a few days. In those few days, I was very vigilant. I actually didn't sleep much, because with the knowledge that the alarm is not present, makes me more focused on detecting the problem myself. As we start adding alarms, the operator gets more information and is able to act based on these alarms that may come up. This is because the operator has so many points to look at that it's not possible for him to watch the entire factory. So we would start assisting him, and the chances of operator missing a key event starts dropping drastically. And we reach an optimization point. Guess what? If we start adding more alarms than what's in that optimization point, we start disturbing the operator and distracting the operator. And his probability of rejecting these events starts diminishing. And most systems are actually configured with thousands of alarms. And we get a situation where the chances are high that the operator will not respond to the situation that's actually dangerous. In our little example, it was where we have the pump not stopping for some mechanical failure. We do take some risk by minimizing the number of alarms. That risk comes from the fact that we do not have duplication of the instrument. So it's possible that the instrument with the alarm could fail, and that would result in the operator receiving no notification of an incident. But we find that that risk is actually very small compared to the risk of him not acting on an alarm because of alarm flooding. I hope that I have given you guys a flavor for what alarm design actually is. It's an optimization problem where we're trying to minimize the number of alarms subject to certain constraints. If you know all of this, why do we still persist and still have this alarm problem? So I often do this with many of our clients, is that we use a strategic framework to try and sort this problem out, as opposed to a pure technical framework. We find that many people, their first go-to is software. They say, okay, let's buy some software to sort this out. And my view is that software will help, but it's not the solution to this problem. This problem is about understanding the culture of your company. So the strategic framework that I have adopted is shown on the slideshow. You can see there's a situation analysis, definition of objectives, a strategy on how to get there, some actions and tactics, and some control measures. It's a simple standard strategic framework. So let's talk about what do we mean by situation analysis. Let's understand the environment that we work in. We work in a multidisciplinary engineering environment. Yes, the problem seems to manifest itself on the control system. Yeah, that's where the problem manifests itself. But the problem is actually a result of decision-making from many, many different areas: process engineering, instrumentation, operations, and safety and risk. Each discipline wants to protect their own interest. No engineer or no technician wants to be responsible for an accident by omitting an alarm. So they will all insist that they have the alarms in. And against that background, in order to solve this problem, we cannot just be control systems and instrumentation. It has to be a multidisciplinary approach. So that comes out of your situation analysis. The second point is about operating culture. We often find that operations typically ignore alarms with zero consequence. They disable alarms without addressing the root cause. And probably the worst effect is to wait for alarms to occur before responding. I had this experience at a factory in Saudi Arabia, where the operator would set all the levels on the columns at 45 and 55%. So I asked him, why does he do that? He says, no, once he does that in the beginning of the shift, he then waits for all the level alarms any level alarm to come up, and then he acts. That is not the correct use of an alarm system. Because what happens in reality is that when you have a transient that runs through the factory, all the levels move. So instead of having one level alarm, he has about 50 of them to deal with. Alarms should only enunciate when the situation is truly abnormal and the underlying equipment has failed. So let's look at situation analysis in terms of culture.
Sit down and talk this out. I would love to. Where will we sit? Perhaps we'll sit on this title of
Hi, sorry, I think there was somebody else online. Okay, so let's talk about the process department. So process department has a knack of adding alarms during risk review. And they do this because they do not realize that they do this because in a risk review, like a hazard meeting, it's the easiest thing to do is to say, safeguard, add an alarm. It's probably the easiest thing to do. They tend to duplicate alarms. And during incident investigations, they would add alarms because you have to put something down in an incident investigation. So you would just add an alarm in there because you have to have some recommendations, and it doesn't cost anything, it's cheap, and so forth. And in doing so, they're creating this problem. And they set activation points that don't make sense. And finally, with control systems. Control systems are not set up with deadbands and delay timers. There's configured duplication, and range settings are all off. So the problem originates from multiple different people. In terms of our objectives, I think the objective is very simple. It's reduce the enunciated alarm rate per operating console to an acceptable limit as specified in EMUA 191 and ISA 18.2. Those two specifications really tell us where we need to be for safe operation. And we need to bring about permanent change in the engineering and operating culture such that the gains are maintained in the long term. In the short term, I can reduce your alarm count like you won't believe. But unless your culture changes, those alarm counts will not be sustained. The problem will return in a few years, and some companies have been grappling with this for 20 years plus. And that's because the operating culture has not changed. If you look at our strategy, it's basically very simple. We have alarm system design, which we discussed. We have bad actor alarm maintenance, which we are going to talk about today in more detail, and we have training and awareness. Who are bad actors? These are some of the bad actors that I know. Alarms are repeatedly enunciated without conveying any new information to the operator. That's the definition of a bad act. So why are bad actors so bad for us? Bad actors are bad because they create a culture where the operator acknowledges an alarm without actually doing any form of analysis or corrective action. It becomes a norm to just acknowledge alarms. And you notice on the operator's panel, the acknowledge button is the one that's worn out. It's literally worn to the bone where there's no keyboard left. And that's because the guy has received so many alarms that he has no way of solving the problem. So alarms are bad for operations. They're a nuisance, they distract the operator. And if you have enough bad actors, we're talking about a few thousand in this little trend, you make your system useless. Useless to the sense that you're better off switching the alarm system off than actually keeping it on. The DCS loading will increase, or PLC bandwidth, and critical alarms are lost in the sea of bad actor alarms. So in our case, we had 6 alarms, but the critical one, nobody noticed. And you can have some adversarial consequences with regard to environment and safety. So there's a real issue with these bad actors. Where do bad actors come from? I'm a fan of Bollywood, not Hollywood. That's just the way it is. But yeah, we get some bad actors from Hollywood. Control system configuration is one of the issues. Process design, the second point, and instrument malfunction. And I often get annoyed when it comes to process design, because you cannot alarm your way out of a bad design. If the vessel is too small for the holdup, the alarm system is not going to help you. You need a bigger vessel or a smaller pump or whatever else you need, but the alarm system cannot solve that problem. And of course, there's instrument malfunctions that will contribute to this. And because instruments are electronic in nature, they have the potential of generating millions of alarms, for example, on a loose connection. Let's talk about the different types of bad actors. So the first type is a chattering alarm. The definition of chattering is alarm enunciates more than 3 times in 1 minute. It's very unlikely, unless you're flying a fighter aircraft, that the process would move at that speed. Most processors would not move to generate new information in a minute. We have fleeting alarms. These are chattering alarms that arrive and go away and seem to come back the next day and leave us again and come back a month later. We have a thing called stale alarms. These are alarms that stay in the alarm log for more than 24 hours. We have duplicate alarms that are configured and duplicate alarms that are dynamic. Duplicate alarms do not convey new information, hence must be removed. Then we have diagnostic alarms. In today's world, with the technology that we have foundation field bus, we have heart instruments, and they have a potential of generating thousands of diagnostic alarms. While those may be important for the instrumentation people, for the operator, they are meaningless and should be sent to different people. And alarms that do not represent events requiring operator action. If there's no operator action, there's no alarm. And that is the first commandment. So how do you go about addressing a bad actor problem? We've broken it down into a few steps. The first step is you need to analyze your alarm journal. And out of that analysis, you would get some kind of identification of the bad actors. That's a list of actions that you are going to take to fix the problem. The reason you would use software is because analysis of this journal can be quite tedious and time-consuming. It's always good to have handy tools to actually help you analyze this data quicker. we don't have endless time to do this. There's a limited amount of time to do this. So we want to do it as quickly as possible. Once we have identified these bad actors, we add them to an action item list. And that action item list is subject to review at a multidisciplinary forum. And that forum includes instrumentation, control, process, mechanical, and whoever else is needed. And in that forum, we hone in on the root cause of this problem. We then get the modifications and approvals the modifications approved and implemented. I think the most important thing that I can say about this particular chart is once an item enters your list, action item list, it's not allowed to leave that list until you have done something about it. In my experience, I find that many companies tend to have action lists running on a daily basis or between shifts and so forth. And you end up with a situation where if the alarm is not a problem anymore, that action item is removed from the list, only to happen at a future date. So the moment you have detected a particular tag as a bad actor, it has the potential to become a bad actor in the future. And that is why you need to address it as once now so that it doesn't happen again. Let's quickly discuss, how do you classify bad actors? Well, the first thing you need is the event data from your DCS. That is when the time that the alarm occurred, how often, and so forth. But just looking at that is not enough. You need the historical analog data so you understand the context under which that alarm was generated. You need the equipment data sheets to understand the consequences of that alarm. And of course, you need the process design, because the process design will tell you whether that alarm is a result of a poor design or a result of instrument malfunction and so forth. Once you've done your root cause analysis, the action is then assigned to the different teams to resolve based on what the root cause of the problem is. Chattering alarms we consider to be the worst offenders. And the solution for these chattering alarms is quite well documented and well known. You need to assign a proper deadband, delay time, process value filtering, and so on. But let's look at some cases. Let's look at the case of a deadband. Without the deadband, operator will get 1, 2, 3, 4, probably about 5 alarms for the same issue. With the deadband, operator will get 1. It's simple as that. Actually, by default, deadbands should be configured on almost every single signal in your factory. And this will give you a big benefit. But a lot of factories are dated, so you have to go retrospectively and do this. Let's talk about the alarm point quickly. So there's 2 reasons to specify an alarm point. The first reason is operational efficiency, and the second reason is equipment protection. We're going to only talk about operational efficiency today, but I think that equipment protection is as important. So the first thing we need to do is confirm that the measurement is self-regulating for load and servo responses. What do I mean by that? If you have an integrating signal, like a level, that signal will never achieve steady state except if it runs at a constant increase or decrease in velocity. So we're talking about things like flows and pressures and so forth. We have to verify that the signal at steady state is normally distributed. This stuff doesn't apply to signals that are not normally distributed. We then calculate the mean and standard deviation of the signal at steady state, which is a standard statistical tool. And the alarm point should be at least 3 standard deviations away from the mean, because we want to minimize the false positives, and we have to minimize it to less than 1% of false positives. So this is a little recipe for you guys if you have to decide where to set the alarm point for operational efficiency. The reason I say operational efficiency is there's often the case where the alarm point has to be set very close to a limit in order to achieve maximum production and so forth. Switches, we don't have deadbands, but we have delay timers. And that's all that you need. You just the delay timers, and they're very effective in adjusting the, in minimizing the alarm. There's a standard table in the EEMUA and ISA 18.2 that will give you the dead time amounts and so forth, deadband amounts. And that's just, I mean, I normally just use the defaults unless there's a reason not to. I don't believe there's a reason to actually do rigorous analysis to figure out the delay time. There's two types, generally on delay and off delay. Off delays are considered safer than on delays, but both can be applied equally. Let's talk about process design. This is an actual example of an actual situation where a RCA study suggested that we have a flow alarm for low flow on this line because they needed a constant sweep off this line. But if you look at this carefully, the action of the controller will move this valve up and down and create much noise in the flow signal because the flow is dependent on the variable orifice that's here. What ended up happening is the operator of the plant had literally thousands of alarms originating from this tag and simply disabled the alarm. And in disabling alarm, he disabled all the recommendations of the root cause analysis of this particular problem. What I'm saying is no amount of deadbanding can fix this. This is a process design issue. It can only be solved by a process design change. Assigning alarms where the operator has to act every minute is ridiculous. The correct solution to this problem was to clamp the valve output to not close less than 3%, which guaranteed the flow down this line at the expense of the pressure. You have to understand the process in order to solve this problem. Let's talk about nuisance diagnostic alarms. I'm going to skip this slide because it doesn't convey much and go to the next one, which is interesting. People ask me, why do you get so many alarms in shutdowns from bad instruments? It's a result of a simple physical property of gases. You see, when we measure flow, we have a restriction orifice and a differential pressure measurement that's subject to a square root extraction. When the plant is off, the sun is shining and heats this side of the pipe, the gas will move that way, end up here, creating reverse flow. And that sends the instrument to produce a signal that's less than 4 milliamps. In fact, it drops to below the setting that the DCS vendor or the PLC vendor has specified to detect a wire break. So it may drop to 3.3, 3.2. Most control systems have a low cutoff at around 3.5 milliamps. This problem is easily solved. You need to adjust the cutoffs or rearrange the transmitter to cater for some reverse flow. Because of the square root extraction, this signal is really jumpy. Let's look at configured duplicates. In the control system, there's much programming and information is transferred from one point to the next point to the next point. You need to be sure to disable alarms at every step. Because when this guy goes into bad alarm, this guy will also go into bad alarm and so forth. So you end up with giving an operator 10 alarms for something that actually is just one issue. So I think that's where the control system people need to take responsibility and sort out the control system. And the stale alarm is probably the most damaging and dangerous of all bad actors. Because once an alarm goes stale, it cannot convey new information. So in the explosion I mentioned earlier, the level alarm went high and the operator continued to fill the tower. And in doing so, because the level alarm was already high, he did not realize how high the actual level was. If an alarm is in your alarm log for more than 24 hours, it's violating the basic principle of alarming. It means that that's not a truly abnormal situation. If you can tolerate something for 24 hours, it's not abnormal. And here is where you need to put some real effort into getting rid of stale alarms, because these alarms have caused quite a few accidents. Let's look at redundant equipment. I think the issue here is we expect the second pump to be not running for long periods of time, because that's why we have it. It's a standby. So instead of causing stale alarms for your operators, consider doing something simple, like using a change of state alarm. In other words, when we change from running to stopped, that alarm will not become stale. Use logic functions. Here we're worried about this motor, but we're worried about less than one running, as opposed to each one having an alarm. Look at command disagree. Command disagree means if I've commanded this motor to run and it's not running, it will generate an alarm. Obviously, if I've commanded it to stop and it is stopped, it will not generate an alarm. And fail to stop and fail to start. Many operators use abnormal alarms instead of change of state alarms. And that really causes a lot of stale alarms in your plant. If you follow proper methodologies and follow the work processes that we know work, you can achieve reductions of 50 to 90% in your plant. But it cannot be done unless you have a multidisciplinary team tackling the problem. I don't think people should feel that they are the only ones that need to do it, especially the control systems people. Often the problem ends up in control systems' hands, but it's actually not control system problem. So really that's where we are. So let's get back our case study and look at the surge vessel. So after a bit of thought, we'll adjust these alarms. So the first one that we need to adjust is the level indicator. So we'll adjust the level indicator to convey the alarm at only 26%, which is below the trip point. So does that even make sense? Well, it makes perfect sense, because it's a diagnostic alarm that if this pump does not stop, it will sound. You must remember, the moment the flow alarm sounds, the operator knows the level is going to drop. It has to happen, because if you're not putting mass into a vessel and you're taking mass out of a vessel, the level has to drop. It's science. It's conservation of mass. How about the start permissive? Well, why do we need that unless we're trying to start the motor? And when the operator is starting the motor, he will look at the graphic and he will see that the start permissive is either healthy or not healthy, and he will start the motor. Start permissive has zero value. There's no operator action to be taken. Why not the trip? Well, if the trip works as it's intended to work, it's a perfectly normal condition. So we do not want to violate our commandments, our first commandment. So we don't need alarm at the trip. How about the pressure? Well, didn't the guy say from the vendor say that he wants a low alarm pressure, a low alarm on the discharge pressure? Well, he said that based on the fact that the pump is running at the time. If the pump is commanded to stop, or the pump is stopped, the pressure signal is irrelevant. This little circuit, where the low pressure alarm is automatically disabled when the pump is confirmed stopped, is available in all the major control system vendors. It just has to be enabled. How about the pump not running? That's an interesting one. What if the pump suddenly stops while we're running the plant? Well, the level will go high. So you'll get an alarm on the level. But if that's not good enough, then you can replace it with an uncommanded change alarm, which tells you that there's something wrong with the motor. An operator can pick that up. How about this flow? This flow will tell you that the valve has failed, the pump has stopped, or no supply. I chose not to include it because valve has failed is a very rare occurrence, and alarm high will tell me valve has failed. The second thing, pump has stopped. I've got something for pump has stopped, so I don't feel I need it. And if loss of supply is the issue, well, I have an alarm for loss of supply. So to end, let's have a look at what happens with the correct settings. I'm going to switch over back for simulation. You guys bear with me, I just need a few moments to reset everything. And if you look at my alarm summary, I have now added a low alarm at 26. I've retained my high alarm at 90. I've removed the discharge pressure alarm. I've retained the alarm on the flow indicator and removed pretty much everything else. So let's have a look and see what happens when we flow, which is fairly normal occurrence, supply flow. So you're going to see a drop in the flow alarm has sounded, warning the operator that there's a problem of supply. The operator will immediately start looking at the discharge at the downstream units. This is not an alarm, just an indication. It's not an alarm, an indication. You can see there's just one alarm. If you look at our alarm summary, there's just one alarm. These are journal items. Pretty cool, huh? One alarm has told you that there's no flow. There's nothing wrong with the bottom of this vessel because nothing has gone wrong. Let's look at the case of where the pump does not stop in this case. And let's see what happens to our process under that scenario, which is a scenario that everyone was worried about when we did the design. So the level will start dropping. At 35, the interlock will come on, but it will have no effect because the relay is fused on the pump. Pump has not stopped, but the level alarm has popped up to give that operator an indication that there's something going to happen to this if he does not act. And if you look at our summary is just 2 alarms. There's a good chance operator will pick up the level alarm and take appropriate action. And in this case, it's actually stopping it in the field, because the relay is broken. So I'm not sure how you guys would have done this alarming. Alarming can be very emotive. But yeah, let's take some questions. That's my story. Kevin, I'll just hand over to you then to deal with the questions.
Thank you very much, Nirmal. Really interesting, the interplay, as you say, between technology and people and engineers from different backgrounds. I've asked people to type in questions, but if anybody wants to speak, that's also fine. I'll kick it off. You talk about using dynamic analysis. Do you ever actually use dynamic simulation to help you do the alarm? the alarm design?
Kevin, we look at a lot of historical data. So we compare the event that we're talking about with if that event happened in the past, because we need to identify where the problem, how the dynamics flow. Personally, I haven't used dynamic simulation rigorously because the number of parameters that we look at generally in a design study is tremendous. There's just too many. So it's not that it has no value. It's just that it takes time, and that is why it's not that often used.
I've got one question here. Let me see if I can actually read it. What software were you using for the demonstration of the process?
Yeah, that's a third-party software. It's not a PAS product. If the participant can just pop me an email, I'll give them the details. It's a dynamic simulation product. Yeah.
Hi, Kevin. Is the presentation going to be available afterwards? And then it went away. Where was it?
Kevin, yes, we'll make it available. No problem.
Yeah. The remark was this was very insightful, especially for me as a graduate, that's really good to hear, because that is definitely a role SACAC's trying to play, is with I guess it's new graduates. We will put the presentation up on our website. I think will be the easiest.
So Kevin, if you don't mind, it's Mike Keller. I don't mind asking a question. Evening.
Carry on.
So when you get large processes and you get a lot of interaction between different unit operations, that's what generates a lot of the alarm floods we have. How do you propose handling that?
There's no golden rule, but the third commandment is your answer to that problem. Because you must always remember that the pipe where the primary fluid flows is not just a movement of mass, it's actually sending information in that pipe. So for example, when this pump stops, it's sending the stop signal to all of these instruments. And that's the wisdom we need in order to eliminate the problem of large interactive processes. Now, following the third commandment, an entire refinery can generate less than 150 alarms per day. Because if you take credit for the fact that the actual material flow conveys information and not be scared to do that, which is what Yoda said, then you can eliminate. And so I'm not giving you a recipe. I'm just saying the philosophy of removing the duplication will get rid of the flood.
Like having to use faster suppression through.
Yeah, you can use suppression, but I find that suppression will give you maybe 20% benefit, but it's a hell of an expensive thing to do.
Okay.
So yes, for the PI, yeah, suppress it at all, as much as you want. That's an easy problem. But suppression, like flood suppression, if a compressor goes down, I think you can get away with just straightforward alarm rationalization.
Okay, thank you.
Yeah.
Thanks, Michael. Anybody else? I'm not getting any typed questions. Anybody else maybe want to ask a question via voice? If not, I'm going to round things up. Thanks again, Nirmal. I think this has worked very well, and I think as SACAC we're extraordinarily pleased at the outcome here, and your part in it. What I would like to ask is, of the 30 people who attended today, if there's anybody who feels they have a subject they would like to give a talk like this on, please let probably Kerry at SACAC know, and we will schedule it, because this is how we become a community of people talking about control problems. And I think it's a great opportunity. Maybe not 7 o'clock. It's too late. But thanks again.
Thanks, everybody.
And also, anybody feel free to write to me as well. And Nirmal gave his email address there.